Welcome everyone to another OCP Tap call. This is call number 129. Today we have Will Creswick from Microchip, which is going to give us a presentation about the latest with chip scale atomic clocks. A little bit about Will. Will is a principal engineer of product marketing in the frequency and time systems known as FTS business unit at Microchip Technologies. He is responsible for managing rubidium oscillators, GNSS discipline oscillators, and test sets. He also supports numerous atomic clock products, and he has co-authored several papers on their applications. Previously, Will worked in the defense industry, researching and modeling radio frequency and microwave technologies. He earned his master in electrical engineering from Boston University and his bachelor in electrical engineering from University of Massachusetts, Lowell. So with no further ado, Will, the floor is yours.
Okay, thanks for the introduction. Yeah, so today I'm going to give a little background on chip-scale atomic clock technology, specifically the technology developed at Microchip, and kind of go through the current state, and also want to give a little update on what we're planning to do in the future version of CSAC, which for now the project is called CSAC 2.0. I'll just do a couple of quick background slides before I get into the heart of the presentation, which is really focusing on CSAC 2.0 and the future. But for those who are not too familiar with the CSAC, this kind of explains it in a single slide here. And so what makes CSAC a CSAC is its low power, about 120 milliwatts maximum power consumption, and it's small size. So it is, CSACs are, they are the lowest power commercial atomic clocks available on the market. It's an atomic clock because it has accuracy, or very good atomic accuracy, within a couple of minutes of powering on. So warm-up time is about 180 seconds. And you can see this on the bottom left here. This is short-term stability, frequency stability plot, or Allen deviation. You can see it's about a part in 10 to the minus 10 at a second, and flickers out in parts of the 12 in about 3 to 5,000 seconds. These clocks do drift. They're not primary frequency references like a cesium beam tube. So you can see they do have some drift. So over the course of a day, typical frequency drift is, or over a month, typical frequency drift is about 3 to 9 parts in 10 to the minus 10. The top right, we have kind of a look at the, this is like a marketing slide or picture here, but what it's trying to convey is, this device can operate over wide temperature ranges, and it has very good temperature stability. So typical temperature stability is. Is there a question?
For about 20 seconds, your audio broke up. Are you possibly on a wireless link?
Oh,
I don't know if you have an Ethernet port handy or something, but
yeah, maybe I'll kill my video for a second. That might help with the bandwidth. Let's see. There we go. Oops. Okay. So I don't know where you lost me, but I was just kind of going over the typical frequency stability on the bottom left of a CSAC, and then some of the features here are its frequency stability over temperature, and a 1 PPS function for a calibration to a primary reference clock. And then finally, it's very rugged package. So I'll show the physics package in another slide or two, but you can see it's a vacuum sealed design and it can tolerate up to 1,000 Gs. This is a timeline of the CSAC development. So it was co-developed with DARPA and others from 2000 to 2010. And then the model SA45 was released in 2011. And then after that, a couple of other variants were released. So in 2014, a low noise version, 2019, a space version, which is rad tolerant. And then a major design update was in 2021, where the model SA65 essentially replaced the SA45. And that was primarily to increase the temperature range and improve the stability over variable temperatures, as well as some electronics updates to improve DC noise handling and some end-of-life components. And then a couple months ago, we released a new version of the low noise CSAC. It's called the SA65LN. Here's a little cartoon of the physics package for the CSAC. You may or may not have seen this, but CSACs do start their life as a wafer to produce the cesium vapor cell. And you can see how it's put together here, where cesium is deposited onto a substrate, and then another wafer is anotically bonded on top, a Pyrex wafer on top, and that makes the glass vapor cell, which you can see in this blue cube on the right side here. And then at the bottom, there's a VCSEL, so vertical cavity surface emitting laser, stimulates the cesium atoms, and a photodetector is on the other side. Some of the other key parts here are the suspensions, and this is all placed inside a ceramic assembly. Not pictured here is the C field coils to keep out magnetic fields and to set the magnetic fields required for CPT interrogation. Some of the other things, so this physics package, you can see it's populated onto the a PCBA where all the control electronics are. And some of the main components here are a microcontroller, digital synthesizer, and a TCXO, which provides a 10 megahertz output. So this TCXO is always being corrected and steered to the stability of the cesium atoms within the physics package. I'll just show maybe one plot on kind of simulated performance here. So this is what a lot of folks in timekeeping industry are interested in, which is the accumulated time error or holdover performance of a CSAC. So this is a profile from going over about 2.5 days. And we're simulating a 20-degree temperature swing. And so with the legacy design, we were getting about somewhere from 30 to 50 microseconds holdover over 2.5 days with this type of temperature profile. And the SA65, again, uses pretty much the same physics package. Sorry about that. But its improvements in control electronics improve the temperature stability. And so that alone improves the holdover capability quite a bit, about 25 microseconds. And that's kind of a worst case scenario based on the maximum frequency errors due to temperature and drift. Typical performance is more like 10 microseconds. Okay. Oh, skipped ahead again. 2 slides on the latest LN CSAC. So what's interesting about this is it uses a very low power and, more importantly, a low profile evacuated miniature crystal oscillator. And so this allows us to reduce the height of this to about 1/2 inch, which is important for narrow VPX types of chassis. But what you're getting with this, essentially the EMXO is replacing the 10 megahertz TCXO. And so now you're getting the benefits of OCXO or an EMXO crystal purity. So very clean signal, 10 megahertz sine wave signal output, which is always corrected and steered to the cesium atom. So it's kind of best of both worlds, I suppose, depending on your application. It's important for frequency mixing. So this is kind of an example phase noise plot of the LN CSAC down here versus our specification for a microchip version of CSAC. Some of the markets that are pictured here. So, low power is driving most of these applications. So a lot of battery powered remote sensing applications that want to increase their mission times as much as possible by consuming as little power as possible. And, atomic stability, what that gets you is lower frequency and phase drift, I suppose, versus perhaps a crystal oscillator or other technology. And again, you can have both longer missions and then longer times between recalibration of the holdover oscillators by having atomic stability. And then height, I mentioned. So this is all great, but I got to point out the negatives, which is the cost for most consumers is quite prohibitive, so list price for a CSAC for a single unit is north of $5,000 published. At quantity, typical average sales price is about $2,500. So that's kind of therein is the goal or the motivation for the next generation of CSAC, which is to lower the price for everyone and make it more available for all sorts of applications. So before we get into that, let's take a look at some of the major costs from the microchip version of CSAC. We've got it broken out here. And so a significant portion of the cost is due to the electronics and packaging of the CSAC. So the image on the left is showing an exploded view of the assembly. And so the plan here is to consolidate a number of the various control circuits into application-specific integrated circuits, or ASICs. And so that can be manufactured at high volumes and at much lower costs than sourcing the individual components by themselves. And then for the packaging, so we use a somewhat expensive mu metal lid and base plates, which can be quite expensive. So we want to go over and utilize a lower cost, high volume configuration and materials that are readily available in the industry today. And so we have a strategy to do that. And then meanwhile, the majority of the cost of the CSAC is associated with manufacturing of the physics package on the right side. So where the VCSEL and the thermal mechanical suspensions themselves make up a large portion of the costs of the subassembly. And so this cost is primarily driven by device yield that is required at desired specifications needed for atomic clock. So all of this was meant to be addressed in this next project, CSAC 2.0, which is where this brings us now. So this is kind of a high-level overview, but we've got the primary objective up top, which is to develop a CSAC which is able to be produced in massive volume at an average sell price of around $300. We have program goals on the right side of the table here versus the current state of the technology. So you can see there's some modest improvements to.
Hello.
Oh,
Good evening. The commodities. No. Apologies.
That's all right. I didn't want to be rude.
Yeah.
All right. Just the commode.
Yeah, thank you.
Stephen, can you mute your microphone, please?
Trying to, sorry, apologies.
Or maybe the host can if they have permission.
I do not, unfortunately. Anyways, so yeah, so some of the goals are improvements to performance, but those are kind of secondary goals compared to reductions in cost and scaling up manufacturing, and then followed by reductions in power consumption. So you can see this, the current device consumes 120 milliwatts. We're targeting 70 milliwatts or so for CSAC 2.0. We do have some stretch goals to increase the operating temperature range, and we have some sub projects to address that as well within the physics package. Which brings us to the physics package. Oops. Let's see, did I skip one? Okay. So this is a little cartoon of the concept for the new physics package. It's being called the horizontal inline physics package, or HIPP for short. And it's kind of a reimagining of the existing physics package, where we're utilizing wafer scale technologies to lower the overall costs. And so by constructing the core as a stack up of 6-inch wafers, over 1,000 core devices can be made consistently and in a relatively short period of time. These stack ups could then be diced into individual cores that can be mounted onto lower cost suspensions. These LCCs can then be installed on a PCBA along with the components that drive and control the physics package. So you can see, if you're familiar with the old physics package, you can see now it's laid down on its side. And this has the added benefit of reducing the overall height of the CSAC. Cesium vapor cell filling is also being addressed in this project. So that's one of the variables that can impact yield and overall performance of the CSAC. So the image on the left is an automated robot that is capable of dispensing controlled amounts of aqueous cesium azide solution. And the image on the right is a silicon wafer with over 1,000 etched cells ready to be filled. The wafer has a glass bottom that can be analytically bonded to silicon. Then after filling, another glass wafer is placed on top and analytically bonded to the silicon to seal the cesium azide and backfill with buffer gas at the same time. Then the bonded wafer goes through dissociation process to separate cesium and generate the nitrogen gas generated to perform the correct buffer gas mixture. So we've done some experimentation with this and showed very good homogeneity across the wafer. So this is kind of an example of how we check that. And so basically, after the tablet is filled, bonded, and dissociated, we're able to measure the buffer gas pressure in situ. And on the right side is kind of a sample waveform of the cesium absorption. These are essentially unitless numbers here, they're DAC counts, but it gives us an idea of the quality of the absorption and to make sure that we have the correct amount of cesium in each cell. And this is done with laser spectroscopy. So here is a photograph of one of the first prototypes of the HIPP. And so we've circled on the left side some of the key elements. So we have the vapor cell and photodetector and cell heaters on the left. And then the highlighted section on the right is the core subassembly containing the VCSEL, its heater and optics that are necessary for atomic interrogation. The electrical signals to and from the core components are transferred across suspension, then down to the LCC terminations. When it's mounted into a printed circuit board, the signals are then connected to their respective control circuits onto a PCBA. So after we received some of the first prototypes, so the picture on the upper left here, we were able to load one into a custom test fixture here and measure its functionality and performance. And so a couple things about this. So since these initial prototypes are not vacuum sealed, the entire fixture was placed into a vacuum vessel in this bottom left photograph here, and hooked up to a 2-stage pump to draw out the air, simulate a vacuum sealed environment, which is what we're aiming to have. Then these ports on the vessel could then be connected to the control electronics. And then we were able to, with the control electronics connected, we were then able to achieve atomic lock with the physics package and measure its performance. And that's what we're seeing on the right side. Again, an ADEV curve. And so this is showing 1.670 minus 10 at a second, which is in line with current state of CSAC performance. The heater power, evacuated heater power of this physics package was about 27 milliwatts, which was close to or even slightly higher than the typical heater power we're seeing in existing CSACs, but it's still well within our control capabilities and overall won't affect our overall power budget. Okay, so that's the approach with the physics package. Now onto the electronics. And before I go on, I want to give kudos to a number of folks who put these slides together. Presentation has gone through a number of iterations. Mike Silvera, the hardware engineer, and Peter Cash put together this most recent version, which I adapted. And they adapted these slides for Mr. Robert Pletwack, of course, before them. Anyways, the approach here is a multi-stage plan. And so basically the overall goal is to reduce electronic system cost and size. So multi-stage plan was put in place. First stage, we call it CSAC CV1, which integrates the new microwave synthesizer ASIC into an existing CSAC, thereby replacing the whole microwave synthesizer chain with a single component. Also incorporates lower supply voltage circuitry where possible to reduce the power consumption. Then the second stage, which we're working on next, is V2. It's a variant of this first design that integrates the inline physics package now with that synthesizer ASIC that we're testing out. And then stages 3 and 4, which we call CSAC D, V1, V2, they then take the next step by integrating a mixed signal ASIC along and add that to the synthesizer ASIC and fold that all into a single component. And so as of this date, we've completed the development and testing of the first stage, and we've completed the design for the second stage. And we're in the process of testing. This is kind of a look at things pictorially here, or a flow chart, where you can see consolidation of all of these discrete components into the ASICs. And then note that the footprint is also getting smaller over time, where finally we're hoping to end up with a footprint like this all the way on the right side. Okay, so how are we doing this? So this is the synthesizer ASIC. And so if you take a look at the existing CSAC SA65 PCBA, we have this is the microwave synthesis chain circled in red. And so all these parts together were being designed into a single ASIC into a standard 4x4mm 2FN packaged IC. And it's about the same size as one of the ICs in the existing synthesis chain right here. So this contains the gigahertz VCO, a fractional N PLL, and controllable RF power and output amplifier. It also has digital interfaces for precision control of the microwave output necessary for good atomic clock performance. So this is the measured result of a CSAC here. So this was significant effort to get this first batch of ASIC designed into an existing CSAC platform. So the image on the left shows the platform with the ASIC highlighted. And so we were able to achieve atomic lock with the existing SA65 physics package and PCBA with the synth ASIC. Excuse me. Sorry, I'm a little under the weather here, but we're getting towards the end. So this is our first measured result. One of the key things here is the power was reduced to under 80 milliwatts. So that's a big improvement. Okay. Any questions so far? Maybe I'll stop for a second. I've kind of gone through a whole bunch of stuff.
Yeah, let's see if there's any question from the audience. Please unmute and ask the question.
No, I had one. You covered how you're doing for the CSAC2, the wafer-based method. How are you fabbing the chips prior to that for the CSAC version 1?
Yeah, so we're working with the Mayo Clinic, and they're developing the ASIC technology for us. So they're developing the early prototypes.
No, apologies. You're talking about for CSAC 2.0, they're doing the early prototypes?
That's right. Yeah. So this ASIC that I was just showing here.
Mm-hmm.
Oops, skipping ahead. Yeah. So we worked with them, and they collaborated with us to come up with this design for the synthesizer ASIC. And so the idea is to develop these and then port the technology over to large scale manufacturing.
Oh, no, okay, but for the prior, where you're talking about building the actual, I think, vapor deposition cell with the cesium atoms, you talked about using wafers. Were you not using wafer tech for the original version of the chip, the CSAC version 1.0?
Oh, I understand. Yeah. Yeah. So for the physics package, we are using wafer technology for portions of it, but the idea, so like, I don't know if you saw that first slide, but we were showing the vapor cell itself was developed with vapor technology, but now this new approach is using multiple wafers and dicing them all at once.
Okay, understood.
Mm-hmm.
And then another one I was curious about, where you're looking at potentially increasing, I guess, the number of sales units. For a lot of the people in this space historically, it does tend to be like defense and some of the others. What about targeting more data centers, where then the size and the power consumption isn't as big a concern? If you mentioned like the quality wasn't necessarily as good. If you could put 5 of them on the same PCB and then somehow average them together, would that be sufficient or not really? I don't understand the sense of what the actual defect types are. Is it completely failing, or it's outside of tolerance, but you could merge them and then compensate for it?
Yeah, I suppose if you reduce the size and the power enough, you could kind of do an ensemble, I guess a miniature ensemble of number of CSACs or any oscillator onto a single PCBA and
And, and
improve the-
I'm not sure you'd even have to reduce the size either. I mean, sometimes you're buying these massive NICs that are like 2 PCI Express slots deep. It should be big enough to fit easily, especially if you do like a full length PCIe or you even went to like a 1U or a 4U server. I'm just comparing it to the cost if you want to buy like a regular cesium reference for you. You're talking tens of grand. So typically no one gets one, but if everyone could get one of these and they have to sacrifice 1U, but then they have a guaranteed clock and frequency reference, that could be very interesting for other communities that care about things like time synchronization.
Yeah, sure. Yeah, I mean, you just got to be careful because it's not a cesium beam tube, so it'll never achieve that type of frequency nominal accuracy or stability. It's really meant to provide, microseconds of holdover for a couple of days. Yep.
Okay, so you're not looking at like sub nanosecond necessarily, so assuming you're continuously disciplining it to a GPS signal.
So, yeah, if you're continuously disciplining to a GPS signal, that's where something like a low noise crystal might be very advantageous. This is more if you need kind of that, I don't know, more of a holdover performance. So a lot of folks pair this with a crystal to kind of get the best of both. Yep.
Yeah, and then another question, just in terms of the cost, how much of that is a function of the demand? So you're talking about selling like tens of thousands of units. If that went to 20 or 50 million, how much could you, with the existing technologies, bring down the per unit cost? For example, if like every Ethernet NIC sold in a data center suddenly had one.
Yeah. So the goal that we have now is pretty aggressive compared to the existing technology. And so it's to eventually get to a place where maybe 1 million can be produced in a year. Tens of millions might be a stretch.
Gotcha.
There'd have to be some advancements there. So,
Hey, Will, I have a question on that slide you showed where you were summarizing your agreement with the Army. You talked about the prices for 1 million pieces, but your manufacturing capacity is 100K a year. So how would that work? Would they take delivery over 10 years?
yeah, so that's kind of the good catch. Yeah. So that's kind of like our early benchmark for manufacturing capacity, hundreds of thousands a year. And then eventually you'd be able to scale that up if it's successful across multiple factories to get to that 1 million per year type of threshold.
Okay. So those are just like benchmarks right now.
Exactly. Yep.
Okay.
Okay. Okay, I talked about this. So a couple more slides here. We did get in a new, so this is new information here. This is a second version of the ASIC, microwave ASIC that we got in this week. We believe it'll have better power consumption than the prior one, but testing is ongoing. So if this one's successful, this will probably be the ASIC that we use going forward. There are some minor design improvements over V1. All right. So you can see this is the CSAC CV2 platform update. And now you can see a lot more things are starting to get folded into the mix here. So we've got the synth ASIC, a low voltage circuitry from V1 Electronics, replacing, and then we want to replace the physics package with the HIPP design and supporting circuitry. So once the completed circuit boards are delivered, we're gonna install the new physics packages and commence on testing with some electronic and software updates here. Okay. So this is the, sorry about skipping ahead here. This is the mixed signal ASIC. So the primary objective of the mixed signal ASIC is to consolidate and integrate as much of the existing CSAC digital and analog circuitry into a single IC to continue to reduce the cost, size, and power. So the ASIC will be customized to meet our exact needs of the CSAC without compromising performance. A sizable amount of the circuitry is targeted to be integrated into a single IC. So that's this 8x8 package. And this work is ongoing right now. And then again, we'll have an iterative design approach to manage these some of the risks. And so that's why we'll be integrating a few portions of this at a time. So the power supply, conditioning, then microcontroller and ADC, and then eventually signal recovery and health monitoring will be ported over. So that's the iterative process before we come up with our final mixed signal ASIC. Okay, about that. So here's a look at the packaging. So this was another source of cost. So once we have the physics package, synthesizer ASIC, and mixed signal ASIC complete, we want to reduce the overall package size. Sorry about that. So the goal is to have a standard double wide dual inline package configuration, the right side there. And the current estimate is about 8.4 cubic centimeters. Further reductions in height could be possible, but that's the goal right now. Maybe getting it down to as small as 5 cubic centimeters. And so this can be realized by moving some of the smaller, moving to the smaller package, as well as by choosing a cheaper material rather than the nickel alloy that we currently use in the CSAC. Okay. Wrapping it up here. So we've measured CSAC V1 with the synth ASIC. We've received the inline physics package and kicked off development of the mixed signal ASIC. We've also working with our, so Microchip has a big I guess IC company. There's a fab in Colorado Springs. We're working with them on transferring some of this technology to large scale manufacturing. And we're also looking to start our initial manufacturing in Beverly, Massachusetts before expanding it outward from there. Key dates are to have the CSAC pre-production devices in 2028. So yeah, so that's CSAC 2.0. Any other questions?
I've got a question. Maybe you mentioned it and I missed it, but are you guys planning on doing any like shock vibe testing or other fieldable testing beyond temperature testing that you released data for?
So not until we have a final version of the physics package that is able to achieve vacuum. So we should have something maybe early next year on that, but we have not done a shock and vibe testing yet on the early prototypes.
Cool, thank you. This is really great to see. It was a nice presentation. I was really pleased with like the depth you went into some of these steps. It's cool to see how Microchip is going about stuff. Thanks.
Oh, great. Thank you.
I had a question, more a historical note for the SA45s. I remember hearing when those were first released more than a decade ago, but we couldn't find anyone to sell us any of them. Any idea what was up with that? Was that a DoD only pipeline or?
Well, so originally it came out under Symmetricom, and it's been available since what was it, 2009. They did small quantities, and then Symmetricom was purchased by Microsemi, and now here we are, Microchip. But it's essentially been the same overall design with some minor updates over the years.
Were they under any sort of export controls though, or was for military only applications? Because I was surprised all the timing vendors didn't immediately start including them in 2012, 2013. It was always rubidium oscillators for holdover was the best you could typically get.
Yeah, so rubidium is still the best. Microchip makes a rubidium miniature atomic clock. It's about 10 times more stable in terms of short-term stability and accuracy and temperature stability and drift, but comes at a cost of power. So those devices are about 5 watts. CSAC is about 120 milliwatts. So it depends on the application. It's more, CSAC is really targeted for low power applications versus high performance
Gotcha.
applications. Yeah.
So for data center applications, what would you recommend?
So probably rubidium technology it seems to be more ubiquitous, I guess, and it's certainly used in a lot of timing distribution technology. So a lot of the Microchip, sync servers products, they call them, and which is network timing.
Yep.
They use rubidium for holdover, and OCXO, I guess, for shorter periods of holdover.
And that was my next question: is why don't these fill a gap between the OCXOs and the rubidium?
Well, a lot of that is the cost and the price. So OCXO, you can get a pretty good OCXO for a couple $100, or maybe even as cheap as $50 to $100.
Yep.
And the average sales price of CSAC current state is $2,500. So there's a big trade-off in cost.
Yep.
There.
Okay, so the primary use case for this, I assume, is more like in mobile applications.
Yeah, by and large, CSAC is used in a lot of battery-powered mobile applications where power is critical.
Makes sense. All right. This was extremely insightful. Thank you so much for doing this. I've been hearing about these devices ever since I started dealing with time synchronization, but to actually see a full breakdown is phenomenal. So,
welcome.
I have a question. Can you hear me? It's Martin.
Yeah, go ahead, Martin.
You show us the packaging of the CSAT 2.0, and you mentioned you have some material, something to do with something. Could you elaborate a little bit? I couldn't really hear clearly.
Yeah. I kind of breezed through that section. So the physics package has the current CSAC has 2 layers of mu metal shielding. There's the first layer that is immediately around the physics package.
Hello.
Hi. And the second layer is that outer box that covers everything, the cover, which covers the PCBA. And that is also a mu metal housing. So the way that the new physics package is being designed, we see a path where we would just need a single mu metal shell immediately around the physics package. And so that'll allow us to save massive costs in the outer cover and base plate.
and just to make sure I'm hearing correctly, and so people aren't confused as well if they're not familiar with this, you're saying mu, the letter for micro, not new or something else, correct?
Correct. Yeah.
Okay. So I pasted in the chat what ChatGPT said, because you first used that phrase. I was like, what is it referring to? So this is some sort of nickel iron soft ferromagnetic alloy.
Yes. Yep. Exactly.
Gotcha. Well, why are those so expensive if it's just nickel iron?
I'm not really sure. I guess it's part of the manufacturing process, but they do need to anneal it, and so it is kind of delicate versus, say, standard.
Okay, so it's not the raw materials itself; it's more the level of precision of the manufacturing with the fundamental inputs.
Right, and the annealing process. Yep.
Gotcha.
Okay, so the question now, you're saying that you replace that conventionally we do 2 layers of mu metal for any atomic clock minimally. Now you are reducing 1 layer of mu metal to trade up with the performance, magnetic sensitivities versus the cost. Is that correct? Or you do have a way saying that you have a 1 layer of mu metal, you are able to achieve the same performance?
That's right. Yeah. So if you look at the screen here, I'm showing the existing design on the left. And so this lid and the base plate, as well as this shield here, top shield and lower shield, those are all mu metal. So now we have a better way of attaching the physics package to the PCBA with next generation CSAC, where just the top shield and the lower shield will be necessary based on what we're simulating so far. And some reason for that. So if you look at this top shield here, you can see there's some gaps. And so as that gets attached to the PCBA, there are some holes there. And so it kind of ruins the properties of the shielding effect. And so by engineering around that, doing it better, we no longer need a double layers.
Yeah, I'm surprised you have those gaps there. Can't you just rely on sort of BGA to hold it together?
Not quite. So this, I don't have a good picture, but this goes over the physics package, and then there are some holes in the PCBA.
Like viaducts or
yeah, they go down, and then the lower shield gets attached from the bottom to kind of clamp it together. So, but because it has to reach down through the PCBA, it's not continuous. So that's where some of the flaws are with that existing design.
And then there's a next question for this one. In addition to mu metal, you're looking for not the technologically. So look at the CSAC performance, and then if you're comparing to map performance, and then other timing devices, what do you think? What's the CSAC laid on? What's in the market? What's the application? You mentioned about pull over backup for low power. And then this doesn't really look like data center one decider, but then you make it much smaller, so your cell is smaller, so your ADAP is definitely going to be decreased, right? And then what's the purpose for this? What do you accept the military is saying we want to CSAC? What do you think this is going to be in the market in the future? What application laying for in the future?
Yeah, I mean, just by reducing the size and the cost, it really does open up a lot of applications that have kind of been closed off and that are price sensitive now. And so, you know, think of vehicle usage. And so putting a CSAC at $2,000 or an atomic clock in there, it just wouldn't happen. But if you reduce the cost, then now you're opening up maybe that type of market, maybe not consumer vehicles, but maybe you know, everything else, trains, buses, you know, taxis, things like that.
UAVs, cruise missiles, other things in GPS denied environments along certain borders.
Right. Yeah, exactly.
Right. A $400 drone is the new $1 million cruise missile. So we really need to cut the cost down.
Yeah, you're right. Yeah. So yeah, so it's those types of markets that that could use atomic accuracy or a frequency reference, and that maybe are price sensitive, and then, you know, the existing users would love less power. You know, that's what everyone asks for, is lower power, because they want to have longer missions, and that reduces deployment costs. You know, if you drop your remote sensor somewhere and then you have to pick it up every 2 weeks, you know, it's expensive to have your ship pick it up or a truck pick it up. But if you can leave it out there for a month, then now you're reducing those costs of
costs.
yeah. anyways.
How small do you see eventually as you continue to iterate your
Yeah, that's what I was wondering.
processes?
Yeah, so that package that I was showing before, there it is here. This is the concept now, about 8 cubic centimeters. And we do think there might be a path to reduce it a tiny bit more. But that's what we're looking at. So a lot of what's driving the size now is the physics package itself.
But still, the physics package looks like, I don't know, probably smaller than a quarter of that volume, more probably 1/16 of the volume. So what is really is that perhaps like the volume that it stops you to take all these electronics that are left and, let's say, I don't know, sip them, or let's say have a monolithic, let's say, design where you have all of them consolidated in one chip, like, and then put the whole thing like under that physics package. Like, I just want to understand what is preventing it. Is that just volume and price, or there's some physical limitation, like there's some physics that is not budging here?
Yeah, well, a lot of that stuff you don't want to put right underneath the physics package because it is, there is a C field coil around that, and you want to keep magnetic fields out. So if you now put your microwave synthesizer chain right underneath it, you might start screwing some things up there. So they do need to have some separation between the control electronics and the physics package. And then the physics package itself, if you make it smaller, then presumably you'd have less cesium atoms to integrate, and your clock is now not achieving the performance goals of the existing CSAC design. But having said that, I showed you one prototype of the physics package. We have another prototype that is also in development to reduce that size a little bit more without compromising performance, but I didn't present that today until we have some more data that we could share on that.
I like the CSAC 2.0 because it can definitely fit in M.2 form factor. So I mean, that eventually can give us the whole time card in the size of an M.2. That's like what I've been thinking about. So, but I don't know, how far are we from, let's say, prototype?
Well, yeah, we're looking at what is it now? I thought it was 2028. Yeah, here it is.
Not bad.
Pre-production devices in 2028.
It's in the horizon then.
Yeah. We'll get you one. Don't worry.
Done one here too, please.
Okay.
So one more question, Will. Like, let's say, I mean, just thinking with no limits, perhaps. Let's say, I don't know, in 50 years, can we expect all of these things will be the size of an existing, let's say, TCXO, or like in an existing, like, like these modules, the SciTime, like, series of like oscillators? Like, can we have this whole thing, the size of those, like, because they have also some MEMS. I'm assuming like the whole thing just like going in a MEMS thing, and like all those interference get like, taken care of. Like, is that something, again, perhaps some performance compromises should be there. Like, there are things that they're not going to change, but just like thinking out of like, with technology advancement.
Well, I mean, that's outside of my capability. I think we have some physicists on the call who could answer that better than I could, but but yeah, I mean, conceivably, but like I mentioned before, right now, some of the things that limit performance are, fundamentals of physics that we know now, which is number of atoms.
So one question that I don't know if you probably answered it and I didn't hear. I always wondered about the CSAC, and I know, but I'm familiar with all of them, Mac and CSAC. So what will happen, or like, what was the reason that CSAC uses cesium? Like if you use in CSAC with the same interrogation method, rubidium, what will happen?
So it predates me a little bit, but it's my understanding that it was based on the wavelengths of lasers.
Let's say if the wavelength,
available.
I mean, you can change the laser and everything and so on. Like, is there an advantage that you're interrogating cesium?
No,
Okay, that was, I want to clarify. Okay.
not for vapor cell clocks. I
Okay,
don't.
yeah, because I mean, I'm usually familiar with the vapor cells to use rubidium, and CSAC is the only one that is different. I always wondered why.
Mhm.
Hey, Will,
Yeah.
the CSAC was developed, as you pointed out, under a DARPA contract, and that started back in 2002. And back then, it was easier to get lasers that matched the cesium resonances rather than the rubidium.
Interesting.
Okay, there you go.
Thank you, Steve. So that's not like driven from like, require physics.
No, it was just
whatever is available.
what could they get in a VCSEL?
Yeah. Thank you, Steve. This really puts this in rest because I've been thinking about this for years and I never had the opportunity to ask.
Yeah.
Wonderful.
So the Mac also uses VCSEL technology now, but
yeah,
I don't think those lasers were available until a little bit later.
Yeah.
Right.
So maybe Steve, like just wondering, now that you're going for a 2.0, why we didn't go for rubidium? Or like there is really no difference, or like that's why we didn't bother, or like you wanted to keep the heritage?
I think again it is the laser and the size of the laser, but I don't know. I can't get it.
It can be heritage, and also I mean the acronym CSAC. Like they even though it's like chip scale, but it sounds like CS. I'm assuming, I don't know, like it's like a double meaning.
Well, it was not driven by the marketing guys.
Okay, good to know. Definitely not. All right. Any more questions? Okay, hearing none. Again, thank you very much, Will, and Steve, and everyone else who helped you with the slides and preparation. And we'll see everyone in 2 weeks.
All right. Thanks, everyone.
Thanks, Will.
Everyone. Bye-bye.
Bye.
Bye.